So now that we've had a look at how it works, I wanted to also show some results because I think they look very, very interesting in that epoch 0 shows you what happens right at the start of training when no clustering has occurred yet. But very, very quickly, we find that clusters form in epoch 1. So this is for the MNIST data set. So there are 10 clusters here. And they kind of stay stable. You know, this dark blue cluster kind of stays in the same position. It just kind of gathers other dark blue clusters as it progresses throughout the rest of the epochs, which I find a very nice property. It's not jumping around. It's kind of found an optimal setting and just tries to work from there. The authors compared this to an autoencoder framework, which is shown as the dark green line here. And I think you can really appreciate what exactly the unit Gaussians add to this particular framework. I mean, the accuracy is significantly better than using autoencoders and other adaptations of this framework, including just the Gaussian mixture models as well. And finally, I think it's really nice to see some visualizations of this compared to other network architectures, including the variation autoencoder, which is shown here, and VaDE shown just below it. We have the Gaussian mixture model. So really, we can see adding some deep neural networks improves the quality of the reconstructions. And InfoGAN, which is another clustering algorithm, which I will touch on a little bit in a few minutes. So first of all, you can really see that there's a big difference by adding the deep component between the Gaussian mixture model and VaDE. And secondly, you can really see that even without the Gaussian mixture model component and just learning a latent space, the same number of clusters, you get something reasonable with just a bog standard variation autoencoder. It's slightly better for sure with a VaDE, and obviously the clustering has worked really well. But the reconstructions themselves don't improve massively. It's rather the grouping of all of those reconstructions that's been improved massively. And InfoGAN does not do that badly either. There are some incorrect cluster instances here, but it does fairly well. So one thing that I do want to mention, and that I came across when I considered using this earlier in my work, is that the authors kind of point out that actually starting off training a VaDE architecture is quite difficult, and they expand on that in equation 17 in the paper, saying that at the beginning of training, the model is so weak that it often gets stuck in local minima or saddle points. And because of that, they actually used a pre-trained model to avoid this. So they trained a stacked autoencoder to pre-train the networks, the auto and the encoder and decoder component of it. And then they added the Gaussian mixture model component after that. So I find that if you don't have a lot of data to pre-train in the first place, this can be a severe limitation. Nevertheless, it is a really nice way of creating these clusters, and obviously works really well if you have the limitations and resources to be able to do this pre-training part as well. And it may be worth just trying training it from scratch just to see if you do get these undesirable local minima or saddle points. And you could probably see that through your loss training and loss functions during training, but also by looking at some filters visually and seeing if you have dead filters as well.
Quick question. What is a stacked autoencoder?
So a stacked autoencoder is almost many networks all stacked one on top of the other. So for those of you who are familiar with multi-layer perceptrons, are almost like many fully connected layers. It's like stacking multiple weak networks on top of each other in order to create a very strong network, which is a commonly used technique in machine learning in general. And it's just been adapted and used for deep learning and autoencoders as well.
Okay, thank you.
So as mentioned, the week 2 exercise will be building a variation autoencoder. I highly recommend using the VaDE that you built last time because there'll be very little modifications that need to be made for it. The only modifications will be adding that Gaussian mixture model component and then adding the loss function. And then feel free to go ahead and visualize them and see what's happening within that latent space. So that's the VaDE a part of this this week's discussion. There are many techniques out there for clustering, and some of them are worth mentioning, and some of them are in the paper, the survey paper that I talked about earlier. One is the deep adversarial clustering technique, which is extremely similar to VaDE in that you have the reconstruction and the clustering term within the loss function. For me, the only difference was that they use adversarial autoencoders as well. So the cross entropy had true and fake generated latent code representation. So it has an adversarial component to the deep representation. One of the other techniques that were mentioned within the paper itself, within the VaDE paper, was deep embedded clustering, and they did actually a comparison with DEC as well. And it's slightly simpler than VaDE in that, A, they use an autoencoder, not a variation autoencoder. And in DEC, what they do is they first train a fully autoencoder from end to end. So you have your encoder and decoder component. And then they throw away this decoder component and then simply use the encoder component to create the clusters. So here they're using a typical autoencoder loss function, and then they switch the loss function to a hardening clustering loss function, as can be shown here. And there's other similar methods to this, which are in this space as well, including DNC and DBC. Feel free to look them up, but they kind of perform a very similar task as to what's shown here. Other functions that are clustering techniques that are worth knowing about is ones that are based on GANs. So CatGAN is well known and uses a generator and discriminator component as well. So if you remember back to last week, a GAN component has a generator which generates examples from what it's learned so far, as well as a discriminator component which learns whether a particular example that has been provided to the discriminator is real or fake. So here, all they've done is kind of extended the output from the discriminator to a multi-class output rather than just the 2-class, as well as learning which cluster does this particular image belong to, but also what's the likelihood of that particular image belonging to that particular cluster. So there's a level of uncertainty as well as actually assigning a cluster label as well. And for each component, they have a loss function defined in order to achieve this. And feel free to look at the paper for further details. And finally, InfoGAN, which was also mentioned in the VaDE paper, kind of comes back to this technique of entanglement, which we talked about also last week. So the purpose here is to learn disentangled features, where disentanglement is actually enforcing high mutual information between codes which are generated. So the idea here is to learn latent representations as codes, or essentially a code book, as well as having the real and fake output from the discriminator as well. So again, there's kind of 2 terms that need to be optimized here. What's also different about InfoGAN is that the input to the generator isn't just the latent code or latent code book, but also some noise as well. And apparently that helps for the generator to build and to be more adaptable to noisy data and to be able to generate clusters that have this high mutual information component. One kind of comment that came up last time during the Lunch and Learn session before we started this workshop was non-parametric clustering. And in reality, it was quite hard to actually go out and find a deep learning component which was able to do non-parametric clustering. And what we mean by non-parametric is that you don't have to learn how many clusters you need. It should be able to go away and do that by itself. So I was only able to find one, actually, and the link is shown here. And it's based on deep belief networks, which is shown here. And they kind of learn a deep belief network as so. So you still have kind of layer by layer architecture where you have hidden layers as you would do in a traditional neural net. And then they kind of switch that off for a while and do this non-parametric maximum margin clustering. And the purpose of that is to, I think the original idea of maximum margin clustering was to extend support vector machines to unsupervised learning by kind of relaxing the idea of learning class labels and rather learning continuous variables and maximizing that classification margin. So by relaxing that property, you're kind of able to adapt and adjust for your data accordingly. The paper kind of goes into exactly how the non-parametric part is implemented, but I don't have time to go through that today. But I would refer you to the paper if you would like to look at non-parametric clustering, but I do warn you that it's not highly researched in this field and there's not a many number of techniques to do this. Okay, so lastly, I want to switch, kind of do a slight switch from deep clustering to predictive modeling, because I think it's a really interesting upcoming field in unsupervised learning, and I think a lot more people are also working on it. So the idea of predictive modeling is to, first of all, it's designed for time series data. So a lot of people who are working in this field are working on videos or 3D animations. And the idea is to predict future frames based on what you've learned so far, and based on the frames that you have seen so far. And one such network, which I'm going to focus on today, is called PredNet, and the link is also provided here. So PredNet is actually inspired by the concept of predictive encoding, which I did look up. And predictive coding is from the neuroscience literature. And the idea is that the brain is continually making predictions as it receives information from lots of different sensory inputs. And so that's really the idea of PredNet as well, to update the predictions that it's making as it sees more information. And what's really nice about PredNet is the authors explicitly state that PredNet is general in that it can be applied to any kinds of data. So it could be applied to text data or any other types of data where you have a time series component to play with. So this is the PredNet architecture, which is given in the original paper. You can see that it has a recurrent neural network architecture here. The difference being that we actually have a generative model component, which is the green box RL. So this is essentially a generative model. I'll show you exactly what it looks like in a minute. Oh, right here. So this box here is a convolutional LSTM. And the output from this generative model is a prediction or a generated frame of what it expects it to look like based on what it's learned so far. And then that prediction is compared, the difference is compared with the actual frame itself, and the difference is noted down and fed through this ReLU and subtract operation. And then that gets fed into the next time component, so AL+1. And again, the process repeats until it goes into the next frame, and so on and so forth. So essentially, it's making a prediction as to what it expects to see, looks at what it's actually seeing, and then looks at the difference between the two frames. Very simple idea, but it's very effective as well. So this red box here, actually, the E stands for error. So it becomes, the difference is essentially the error, which is then fed into the next AL+1. And then contributes towards future frames as it sees more and more information. So you can see where that predictive encoding component came from. So this is a really nice video that the authors provide on their GitHub page, and actually shows you some of the frames that came from real data, and then some of the predicted frames as well for the corresponding actual frames. And you can see that whilst they're blurry, actually it's capturing objects really, really well, like entire objects really, really well, as well as trees in the sky. So it's definitely learning the appropriate and most important information in order to generate new samples, which I think is really exciting. And I think it's a really nice upcoming research in this particular field. And this is all done unsupervised as well, which is another nice component. So that kind of finishes off week 2. And again, as I mentioned last week, I want to finish off with some pros and cons of each technique that we discussed today. So when we looked at clustering, the pros were that we kind of get 2 for 1. We already saw variation autoencoders, and by adding this additional term, we're actually getting clustering as well as reconstruction. So we're accomplishing two tasks instead of 1. We're also learning disentangled features by adding that additional loss function term. And these clustering components are actually visualizable because of that enforcement to separate them out into individual clusters. In fact, you could use the deep embedding projector, which I mentioned also last week, to look at some of the clusters that you learn within VaDE as well, and any other clustering technique. Now, all of that comes at a price, obviously. We're increasing the complexity of the algorithm significantly. And as a result, we may need to train it for longer. We may need a little bit more data, even if it is unlabeled data. The initialization is very poor, and the authors of VaDE also mention this in their paper themselves. So often we do need pre-trained networks. And furthermore, we need to choose K, so how many clusters we need. And whilst I did mention one non-parametric technique, there's not a lot out there. So for the majority of the techniques which are widely used, we need to choose that particular parameter. And then for the predictive modeling part, which I just touched on at the end here, you can really see that we can learn something very rich and very meaningful in an entirely unsupervised manner, which is very, very exciting and has some applications in real-world data. It's not actually that hard to understand. It has a relatively simple architecture. However, it does have many parameters within this simple architecture. Therefore, it is memory intensive, and you do need the computational power in order to train all of those networks and layers and for different time series. And as we saw in the example video, the reconstructions tend to be blurry. So if your purpose is to reconstruct data accurately, it may not be the best way to go about it. But nevertheless, it's very, very exciting, and making future predictions is definitely looking to the future of deep learning. So that finishes off week 2. Thank you very much for joining me. So next week, we'll talk about semi-supervised learning and weak supervised learning, which is an exciting topic. There's a lot in there, and we can't cover everything within the 1 week, but I'm going to try and hit the top techniques that are used and kind of give you a nice varied example, example of all the different techniques that are used in the field as well. So if you have any questions, bring them along on Thursday and we'll try to answer them. If not, I'll come back to you. And remember, we have our practical session as well. So I'll see you on Thursday. Thank you.